Okay, so in the first note, our beautiful new screen now goes down far enough to accommodate the laptop. So that I don't know. It feels like it's lower.
And
Yeah.
it's only off by a couple of degrees
Okay, that's right. There's, if you look at the bottom here, it's almost
Almost
level.
close enough for jazz.
Wait, do you think if I pulled the projector screen down a little bit?
Yeah, I think they did. It
But it's
feels
got that
like it
huge
used to
black line
be.
at the top.
Pardon?
It's got a huge black line at the top. They pulled it down lower and then that block up there. Because before it was right up to the edge.
It was.
Yeah, so they've shrunk the screen.
But then why is okay? I don't. What?
What?
Oh well. Whatever. It seems that at least my screen now fits on there completely, which is good.
Wi-Fi now.
Ah.
Yeah, it's like it connects right out.
Okay. Fantastic. That way you don't have to listen to me. Okay. So.
I'm coding along with you.
Ah. Okay. So we're going to hit two things today. We're going to hit virtual methods, how they're implemented. Finally get to that. And we're going to hit exception handling. So those two things are on tap. Just a reminder that that the homework assignment is due a week from today, not on Thursday. So you have a little extra time for this one. And
Is
one,
it extended or
no, it's just,
larger?
yeah, it's just longer. Give you extra time. Okay, and just let's see. One quick thing about the last homework. I actually got a couple questions about it. You weren't the only one about interclasses.
Okay.
So if you, there's a problem with a couple of you with the last assignment. We had this thing with arcs, oval, and circle. And I want you to have a circle inherit the implementation for an arc without inheriting its interface. And what I want you to use was composition. So what I was aiming for was to have class circle, and then it would have an instance of an arc, and you would delegate methods. So for example, void set left, you'd simply delegate that to the arc. And then on certain methods like set diameter, you would call both a dot set width and a dot set height. And some of you made a very nice alternative try. You used nested classes. So you would put, for example, circle inside of arc or inside of oval. I'm just going to, for the moment, try nesting it inside of arc. And this has a couple issues with it. There's both the design issue and then there's actually an implementation issue. So the implementation issue is that in this case you actually are sharing ARC's implementation, but the problem is that every circle is going to belong to an instance of an arc. And if you create several instances of a circle from the same arc, you'll end up kind of with circle, say C1, circle C2, circle C3. They all share the same arc. And that means they share the same state information. So instead of each circle having its own unique instance of arc, now you have this kind of like pointer prime you get in C when you have several char stars pointing to the same string object. And so when you change the state information for C2, you're actually accidentally stepping all over the state information for C1 and C3. So you're achieving that same goal of having circle inherit ARC's implementation, but unfortunately, because you can create multiple instances of the circle with the same ARC object, you'll end up with this problem right here. And then the second problem is a kind of from a design standpoint. You want, these were meant to be standalone classes, and I want to be able to create each of them just using the new command. I want to be able to say C equals new circle. And if it's nested inside of ARC, you're going to have to do some special stuff as a user in order to create an instance of a circle. And that's not what you want. You want to be consistent. You want to have the same mechanism for creating an instance of an object for all the objects that are in your library. So those were the two concerns with that. Okay.
Circle at variable.
No, circle just had this was the first problem, not the second problem. The second problem was where you had arc size and the like. The idea, it was just, I didn't really go into a huge definition in that problem of exactly what an arc contained. To be honest, I was just trying to throw a wrinkle into the problem, because if I said that I had an oval and you were going to inherit the implementation for it for a circle, it's going to be too much like the rectangle square problem. So mostly I was just trying to throw a little wrinkle into it. Well, good. That means you probably did okay on it. Okay, so moving on to virtual methods and how they get implemented. So, well, if I could get a cursor, that would be very helpful. There we go. Okay, so remember both Java and C++, you could have something like, say, class fruit, and you might have, this is Java, so we'll have a print method. And it's virtual, so it can be overridden. Anyone remember how you make the print method be virtual in Java? No, very good. If I declared it as final void print, then I couldn't override it. But I'm going to have apple extends fruit. And I'm going to have, actually this needed to be public. Public void print. Okay, and the question is, how do we implement these virtual methods? And the way it's done is using something called a vtable. So you'll often hear reference to something called a vtable for virtual table. And if you looked at the way the objects were actually implemented, here's a fruit object. Here's an apple object. And in Java, probably the first entry is going to be a pointer to the class object. So in this case, to fruit, and in this case, to an apple. So in Java, every class actually has a runtime object associated with it that has some information, such as that's where you'd find your class variables or class methods. Then the next entry is typically going to be a pointer to what's called the vtable. And finally, the rest of them are going to be pointers to your instance variables. Okay, so from here on, we have instance variables. And same thing here. The V table contains addresses of the methods that are going to get called. So here there will be a pointer to the print method. So this is actually not the code, but it's an address for the right print method. So in this case, because Apple has its own version of print, that will point to a different print method than the one for Fruit. Fruit will have its own pointer to a print method. So at runtime, what happens when you declare something, say, of type Fruit, if I have Fruit F, and I have a reference to f.print, then the way that gets compiled into the bytecodes is you'll have a jump through the virtual table to the appropriate print method. So in fact, in pseudocode, what it might look like is, say, F entry 1, because that is, if it was an array, this would be kind of 0, 1, F of 1, dot, and now, since the table is itself an array, 0. In some sense like that is kind of the pseudocode. So F of 1 says go to the first entry in F, which is a pointer to the V table, 0 because print is at location 0. And you can see then it doesn't really matter. As long as print in every subclass is in the same location in the V table, you'll always get the appropriate print method called, because if this is if F is a pointer to Fruit, that's fine. If it's a pointer to Apple, it's fine. But in both cases, the V table is at location 1, and in both cases, the print method is at location 0 in the V table. And so no matter what happens, the right print method will always get called. The interfaces, I believe what happens there is that you actually have, let's see, how does that work? It should still work off of a V table, because with the interface you just still should, no, you're right. For an interface, because the problem is when you have two different classes, those two classes could put the method in a different place in the V table. So in fact, you would have to have, in that case, multiple, you'd have to, instead of just the first entry being devoted to the V table, you'd have to have entries 2, 3, 4 for each of your interfaces. Right, so if you had interfaces, now in effect you have multiple V tables. So you're going to, in essence, have to have an entry for each. So your first entry is still your class, and in general you would still have the V table for your classes, and then 2 up to however many interfaces you have. I'll still call them V tables, but now they're interface V tables. So you're going to have one V table for each interface. But then it still works, because you still have, you know which entry corresponds to each interface. So you just assign, like if it's through the one at location 2, it would become F of 2, then whatever was the appropriate entry in the V table. Okay, so basically when the compiler lays out the memory for an object, it's going to start by using the same memory mapping it used for the parent. So basically, if we have fruit and we have apple extending fruit, then the first part of apple's layout is really going to look just like the layout for fruit. And then you'll have whatever additional stuff you have for an apple. And the same thing will be true for the V table. The first part of the V table will be whatever methods were defined by fruit. So it would be fruit's basically V table. And then whatever methods that apple adds. These are added methods. If it overrides a method from fruit, then you simply substitute the right entry into the fruit V table. Okay, so basically you're copying initially, you're just copying the fruit V table into the V table for apple, including all the addresses, because if you're not going to override one of fruit's methods, then you want to accept that method, so you want the same address. Then any methods you override, you go into this part of the V table and you change those addresses to point to the methods you override, and then down here is just the additional methods that you add to the interface. Okay, so apple methods. These are methods added to the interface.
Is this vtable something you have to actually implement yourself, or is this something that's inherent to Java?
Wait, run the first. I didn't hear the first part.
Is the vtable part of the class, is that something that Java implements on its own, or is that something that we need to?
You don't do it, the compiler does it.
Okay.
And the C++ compiler does the same thing for C++ programs. So both C++ and Java compilers basically do the same implementation. So this is what's happening in the compiler. You don't touch this, but I want you to know how it's implemented. Okay, so I have, if I just quickly go to my notes, and implementation issues. So here I actually have the so-called assembly language code. I just basically copied this from the book. So the way the byte codes or the assembly language codes would work is that you would first load the address for F into a register, in this case register 1. So that's the object, F's object, okay? So in C++, you know, if you have F is a pointer to the object, that's the pointer that's going into R1. Then in this case, I was assuming that the first entry in F was the V table. So I know that for Java, I said the first entry was the class object. So, but in C++, the first entry is the V table. So this is basically the code for C++. And if it was Java, it would add 1 times 4 because it would be 4 bytes in. So now I'm loading the V table. Then the third instruction here, R2, I'm assuming that the actual method, which is M, occurs at location 3 in the V table. And each pointer is 4 bytes. And so I'm saying now the address is R2 plus 2 times 4. That gets me my address, and finally I make the call. And this should help you understand why it takes longer to call a virtual method than it does to statically call a non-virtual method. Because with the non-virtual method, it would be one instruction. You would know where it was, and you'd simply call it. Okay, so if this was if this was a non-virtual method, then instead of 4 instructions here, you would see basically, what would it be? It would be some offset off of where the program starts. And the problem is I don't remember what that register is normally called. But normally when you load a program into memory, there's going to be some register that points to the base address for the program. Does anyone remember from 360 what that is? There should be some pointer to your base, to the first address, to your location. No, it's a register that holds the address. It's not the frame pointer, it's not the stack pointer, it's not the program counter. But normally there's some register that points to your program's base address. At any rate, it's going to be, normally, here's some method like M, okay? And it's at some offset, O, from the base register. So I'm just going to say normally the call would just look like something like call, something like base, whatever's in the base, plus O. And it'd just be one instruction.
Register is the base pointer. Link register.
I'm just calling it base. I'm not going to have it. What did you say it was, John?
It was the base pointer, extended base pointer.
Okay.
Register points to the last closed stack frame.
That's not quite it either. It's because it's not a stack frame. It's actually the beginning of your program. I'm just going to call it base. But at any rate, the idea is there's only one instruction versus 4 for a virtual method. Okay. So does everyone understand this, how the objects get laid out in memory? That basically you start always with your base class. And then, so this is your base class, and then you add any instance variables that you define over and above that. And the same thing happens in the vtable. You start with your parents vtable, and then you add any methods. And that's why subtypes can always substitute for supertypes, because the first part of a subtype is always going to be identical to the memory layout for the supertype. Does that make sense? Okay. Then the other thing, I think I went into it, but I'll just say it again. So reason number 1 why virtual methods are slow is because of the overhead of the additional load instructions. So there's 2 reasons. Let's now go to, whoops, not iPhoto. Come on.
Added overhead of what?
Yeah, I was going to type it, except that right now iPhoto wants to come up. So everything is super slow. There we go. Okay. And that's no good. Oh, great. That's even better. Jundo. Okay. Okay, so 2 reasons that virtual methods are slower than non-virtual methods. Okay, reason 1 is the overhead of having to go through the vtable at runtime can add or can require 4 instructions, while a call to a non-virtual method may require only one instruction. Okay, because at runtime, or compile time, because at compile time, the non-virtual method's offset from the start of the program is known and can be hard-coded into the call instruction. And secondly, you can't inline. Virtual methods eliminate the possibility of inlining. Remember that inlining means that instead of calling the function, you simply take the function's code and insert it inline. So for example, if I have a very short function for doing min, like say I have a function min, and it's int min, int a, int b, return a less than b, a else b, well, that could be inlined in your code if you have something like, say, this is now C++, int x and y, cin into x and y, int z equals min xy, cout x or cout z. You could replace this instruction right here with, instead of the call, you could simply say z equals x less than y, x, y. That's called inlining. So it basically opened up the function, took the code, inlined it, replaced the parameter names with the actual argument names. Not very difficult actually for a compiler to do. But that only works if at compile time you know which version of min is going to get called. If you don't know which version of min is going to get called, you can't do the inlining. Like here you could say, well, wait a minute, that could work with integers or floats. Well, not exactly, because the comparison operator, there's a different machine language instruction for integer compare and floating point compare. So for the compiler to really be able to inline that puppy, it needs to know which machine language instructions it's calling. So virtual methods eliminate the possibility of inlining because the compiler cannot determine at compile time which method is going to get called. Now, more modern compilers will do things like using data flow analysis. They might be able to narrow down which objects might be possible at the call site. So they might put in some if-then-else code in order to inline. So it might be if A and B are ints, do the integer version of the comparison, else do the floating point. But oftentimes you can't even discern anything from the analysis, from the data flow analysis, and you're just stuck. So that's it. Two reasons they're slower. It's the overhead of going through the vtable, the inability to inline. If you go to the homework assignment, you'll see this question is there. So you can now answer that question. Okay, it may be slightly different. I may have said in Java that it's slower, but it's also true in C++, it's slower. The virtual methods, these are the two disadvantages. So questions about that? Okay. So now we shall move on to exception handling. And how do I want to go? Okay, I know how I want to go. Okay, so exception handling, you can see this good. So basically, an exception is defined as an unusual event. Could be erroneous or it might not be. Okay, an erroneous event, subscript out of range, access through a null pointer. But in an operating system, an exception could simply be a signal from an input device or an output device, and from an input device letting it know that the input device has some input ready for processing. On the output device may be an indication that it's ready to write again. So an exception doesn't have to be erroneous. Now, in the context of an application language, typically we think of an exception as an erroneous event. We're not an operating system. So we typically think of it as an erroneous event. It's detectable by either the hardware or the software. So can anyone think of what is a hardware exception that's often detected by the hardware? That there's two that I can think of that are very common that an application program that you run into with an application program. Sigfault's one, so access through a bad pointer. Division by zero is the other one that is often detected by the hardware and raises some kind of exception. Then there's software exceptions in Java. Array subscript out of bounds is one. Null pointer exception, yes, because I'm not sure whether that's detected in the hardware or in the software in Java. Because in C, it's detected in the hardware. I'm willing to bet that's a hardware detected exception in Java, but I'm not positive. Okay, but when you get the class not found exception, that's software. When you get a class, well, let's see, inability to convert a string to a number, that's a software exception. So most of the things in Java are software exceptions. In C, they're mostly hardware exceptions, they're signals. In C++, they're actually mostly software exceptions as well. And the final thing about an exception is it may require special processing. So if you have a string and it can't be converted to a number, you may want to tell the user they entered an invalid number, please try again. So typically, you're trying to do something to ameliorate the bad condition. In general, you don't want to exit the program. That's your last resort. You normally want to try to handle it in some nice fashion. Okay. So we say that an exception handler then is a code segment that processes an exception and handles it. And we have examples of exceptions. So some of them, end of file, that's actually one that isn't really a bad one. It's not an error. It normally causes you to exit a loop and proceed with some other processing. So that's usually not an erroneous one. Division by zero, not so good. That's a hardware one. Bad input, e.g. can't convert a string to a number. Another one, subscript out of range, or a pointer out of range. Those are just some examples.
One of our programs, actually two of them, we had to throw in there throws IO exception. What was
going on?
Point there, yeah. What was going on with the compiler?
Okay. So I'll give you a quick explanation now and then a longer explanation later, because we'll get to it. So the idea is that you do not, if some method that you call in Java throws an exception like an IO exception, you have two choices. You can handle it or you can pass the buck. If you pass the buck, you have to tell Java that you're passing the buck by saying throws and the name of the exception. Okay, so just again, it's a quick thing, but if I have void input, or say it was like get number, and I decided I wasn't going to handle an IO exception, right after the parameter list, but before the method body, I would have what's called the throws list. It's the list of exceptions I'm not handling. And it's telling Java explicitly, I'm not handling it, I'm passing the buck up to my calling function. The caller has to handle it. And if the caller doesn't, it keeps getting passed up, and eventually it gets passed into main. If main doesn't handle it, main would have to do the same thing. Main would have to say main throws IO exception, and it would get passed to the Java virtual machine. And at that point, the Java virtual machine always provides an exception handler, normally prints the stack and terminates your program. Welcome. Okay, so early languages like Fortran, COBOL, Lisp didn't provide any exception handling capabilities. And in those languages, you had to handle exceptions by hand. So early languages did not provide exception handling capabilities. And in those languages, you have several options. Does anyone in C, what are some of the options you've used in C in earlier classes? Or that? Okay. So one thing is you can register a event handler. That's kind of unusual. So register an event, that's for signal handling actually in C. It's pretty unusual. Register an event handler with the OS to handle a signal. Okay, that's pretty unusual. So that's rare. But there's two common techniques.
You call malloc and it doesn't return a pointer, you can write a test for that and then use exit.
That's right. So it returns a special value, in this case null. So one technique is to return a special value like null from malloc. Okay, or 0 from A to I. So those are special values that you can test. And if it returns that special value, you assume that an error occurred. You take some action, like John said, you do some special processing. Okay, what's the other common? So that's actually the most common technique, but there's another technique that's sometimes used. Status flags passed as parameters. So sometimes it will return a status flag via a parameter to indicate whether the operation succeeded or failed. And now, similar to what Chad said, but this isn't as formal as registering, is you may pass a procedure. So you may pass an error handling procedure to the function. So that's different, Chad, because with the registering of an event handler, you don't have to pass the function to the, you don't have to pass a pointer to the error handling procedure to the function. It's already been done for you. Okay, so those are the 4 common methods for handling exceptions in languages where they don't provide any special facilities. Okay. And they all have their advantages and disadvantages. 2 and 3 are simple, whereas 4 kind of gives you more flexibility to handle the error in the function itself and possibly continue. So this alternative provides the possibility of, I'll say, healing the exception locally and continuing with execution. So that's the advantage of that approach. Whereas 2 and 3, basically you detect the exception and you exit. So you don't heal it locally. You're basically passing the buck. So 2 and 3, they kind of pass the buck back up to the caller. So I'll say that techniques 2 and 3 pass the buck up to the caller, whereas techniques 1 and 4 allow the function to handle the exception. Okay. I'll say locally. Okay, now the difficulty with 4 is that if you have several exceptions, now you have to start passing multiple procedures and it can start to get a little bit clunky. So the disadvantage of 4, so I'll say here disadvantage of 4 is that if you have a bunch of, if several exceptions must be handled. Okay, so we're back. And let's see. I had a typo. If several exceptions must be handled, then you must provide an exception handler for each exception. And it can get clunky. Okay. So that's one thing. Then, for those of you who've taken 360, you were introduced to one other technique that you can use for basically breaking out of multiple. So sometimes these techniques are going to return just one level up the stack. That is, if I have hello. So if my call stack is like A, B, C, D, E, main. Okay, and I have some exception, it's just going to go back to B. Sometimes I might like the call stack to get popped all the way to E. That is, the exception should be handled in E, and all the stack frames from A to D should be popped. Does anyone remember in 360 you probably saw a technique? Set jump and long jump. Okay, I know some of you are taking 360 this semester, so you may not have seen the technique yet. So I'll write it out. So another technique is set jump and long jump. Okay, and this is C. Actually, I'll say C because that's what it is. You can use a technique called set jump long jump. And I'm going to show you the code and then I'll explain it. Okay, so just let me write the code and then I'll talk about it. Okay. So the set jump command, it stores several important pieces of information that are required to restore program state into this buffer variable. So normally you will have malloc a piece of memory, and buffer points to that piece of memory. And set jump is going to store some registers like the program counter, the stack pointer, the frame pointer into this buffer area. Then set jump is going to return 1 for true. Okay? And it's going to, I know in the notes I said it returned 0, but it really should return 1. Does someone remember, doesn't set jump return 1, not, or did I mess this up?
The first time, I think it returns 1. Oh, yeah, it does return 1.
Okay, I thought so too. So my notes have an error that says it returns. I'll check and make sure, but I think set jump returns 1. I'm sorry, it does return 0.
0?
Yeah, because I have a not. I wasn't seeing the not. See the not up there? So set jump really does return 0. So the not inverts it, and you end up executing your protected code. And if an error occurs, right, then if an error occurs, we call long jump and give it the buffer. And long jump is going to restore the frame pointer, the stack pointer, the program counter, and because the program counter points to the original set jump command, it actually resumes execution up here at the if statement, but now set jump returns 1. So long jump, when it executes, it causes set jump to return 1, which now, because it gets inverted to a 0, causes the else to execute, and we go into error handling. Okay, so I'll write that down now, what I just said. So set jump stores registers, including program counter, stack pointer, and frame pointer into buffer. Okay, buffer should be a malloc piece of memory. I don't know. I'm actually not that familiar with set jump. Yep, that's Doc. Is he teaching 360?
No, but Juan said that he went through his graduate systems class without writing a single function call, but only used set jump and long jump for everything.
Wow. Okay. So yeah, I don't know what the right malloc is. So it's just you can ask. Okay. So the first call to set jump returns 0, and hence you end up executing the protected code. Okay, then long jump restores the registers. I'm sorry, yeah, restores the registers from buffer and hence pops any intervening stack frames. So long jump doesn't have to appear here. You could have several functions. So you could have the protected code. So you could have protected code call, say, function, let's say this was in function D. So this might actually, instead of the protected call, whoops, is that okay? So the protected code might actually make a call, say, to C. C might end up calling B, which calls A, and A might actually be the one with the long jump instruction. And now we're here in D, let's say, and so we actually end up popping A, B, and C and ending up in D again. So that's why it's called a long jump, because you may be actually jumping out of several stack frames. Okay, so down here, long jump restores the register, so you end up, okay, so that means you end up, come on, where are we? Dumping, please. Okay, there we go. Okay, so long jump, so we end up back at the original set jump call. Okay, this time set jump returns 1. So we end up doing the error handling. Okay, anyone remember what the problem with long jump is? There's one nasty thing that long jump has as a side effect when it starts popping those stack frames. You may not have discussed it in 360. Okay, so when you pop those stack frames, they may have had values in the registers that had not yet gotten pushed to memory. Okay, because the compiler tries to be efficient. Every time you do an assignment statement, the compiler does not automatically write the value out to the variable. Instead, if it knows it's going to be reused shortly, it will keep it in register and it won't write it out maybe until the end of the function. Okay, that's not bad with a local variable. It's okay for a local variable to get clobbered. But if the write was to an element on the heap or to a global variable, well, when you pop those stack frames, the write will never get done. Those registers are blown away. So you could end up losing some legitimate writes that should have been made to memory. Yes, you can. So let me, first of all, just write that out. Okay, so the disadvantage of long jump. Okay, so I'll say problem is that when the stack frames are tossed, then you may lose, or well, say any values that were held in registers. And not yet written to heap memory or to global variables are lost. Okay, so you could have made some successful changes, but you lost that. And now the question was, is there a way to counter that? And the answer is the programmer in C, the programmer may declare a variable as volatile. Okay, that's a keyword, volatile. So if you have, for example, volatile int x, that means that you expect it to be written as soon as it's changed rather than stored in a register. Okay, you shouldn't do this to a local variable because you don't care. A local variable's value is irrelevant when it gets pitched. But a pointer to something is not irrelevant, nor is a global. Okay, so something like volatile int x, that would cause a write, or if it was a global variable. Okay, so volatile forces a write every time an assignment occurs to that variable. Okay, the problem is you pull this stunt too often and your program slows down a lot. And it's not just because it's a lot, okay, so for one reason, it's a lot slower to write into main memory. It's a lot faster to write to a register. The other reason is more subtle. You may stall the pipeline because a lot of the modern processors are pipelined. Well, as soon as you start writing to memory, you clobber the pipeline. So there's two bad, okay, so drawbacks of volatile. Okay, A, one, writes to memory are much slower than writes to registers. And two, you interrupt the pipeline. Or you stall, may interrupt the pipeline in modern processors. Okay, it's called stalling.
Do you have a specific example maybe where you actually use volatile for a good reason?
I've never used volatile because I've never used set jump and long jump. So the answer is no. I don't have a good example. But my probably best example is you have a global variable where you're lazy and instead of passing the variable through parameters, you just made it global. And so you had some subroutines changing the global variable, and now you're jumping out and the global variable, the changes get lost. So that would be my example. Okay. So we all good with that? Why? So basically, there's ways to do exception handling in C, but they all have drawbacks. And it would be nice, I guess more modern languages kind of took note of this issue and realized that maybe it would be better to have some built-in structured exception handling as part of the language. So the first language that did anything about it was PL1, which none of you have programmed in, but it means something to me because when it was introduced in the early 80s, I was an undergraduate, and we used PL1, and it was going to be IBM's solution to at that point, everyone was worried about the fact that there was language divergence. All of these, at the beginning of time, there were three languages. There was Lisp for AI, there was Fortran for numerical purposes, and there was COBOL for business types. But in the 70s, it started splintering. All of a sudden, everyone was developing these different languages. And that was a real problem for IBM because IBM didn't want to have compilers for all these different languages. They really just wanted to have a single language. So they set about developing the one big language that could be used for business or AI or numerical computing, and it was called PL1. And it could have also been called the kitchen sink because it had everything in it. And it was huge, and it was unwieldy, and it was slow, and it died quickly. So it was an experiment that didn't work, and as we all know, we now have literally thousands of languages. And you just use whatever language you want, but you have to find a compiler that works for that language on your machine. So at any rate, one of the things they did do with PL1 was they did introduce exception handling mechanisms. And they did what was called dynamic binding. So we'll say exception, so more recent languages incorporate exception handling facilities. Okay, PL1 was the first modern language to do so. And its thing was something like, I think it's on condition, and then the error handling code. Or actually, it was a statement. So you got one statement. And usually it was a go-to. For obvious, usually this is a go-to because you want to do more than just a single statement. So when the compiler read it, it didn't execute it. It just took note of it. So condition might be, for example, condition might be EOF, okay, or division by 0. So the compiler makes note of this code but doesn't execute it. It basically takes it and puts it on a list of exception handlers. Then whenever this condition is raised, this statement gets executed. So the compiler makes note of this code, adds it to an to a list of exception handlers, and executes statement when the condition gets raised. Okay, so this is called dynamic binding. Okay, so this is called dynamic binding of the exception. It's basically context free. Regardless of what function raises the exception, this statement gets executed, which isn't always what you want. You may want different, depending on the caller and its context, different callers may do different things with the exception. Okay? So it should be clear you can have multiple EOF conditions from different files. So depending on which EOF condition occurred, you might want to do something different. Or if you have a number that couldn't get converted, a string that could not get converted to a number, well, the context is going to determine what error message gets printed. So this is kind of a nice first approach, but it's not specific, it's not context dependent. So more recent languages use lexical binding of exceptions. And that means that the exception handler is going to be bound to a function. Okay, so exception handler gets bound to a function. PL1, you can see it's not bound to a function. It's independent of anything. Okay, and the idea of having an exception handling facility is that you raise the exception in one part of the code, and then you handle the exception in a different part of the code. Okay, so the idea is you're kind of running along in your code. So you have blah, 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 if error, then throw exception, and then you can continue with your normal code. So the idea is that in C, if you have an error, you often handle it right then and there, and it kind of interrupts the flow of the code. The idea with exception handling is you just check for the error condition. If it's there, you throw the exception, but otherwise you proceed with normal processing. Okay, and then your error code is isolated error 1, exception 1 handler, exception 2 handler. Then your handlers are all clustered usually at the end of the procedure. So your error handling is done in one part of the procedure, usually at the very end, and then you do your normal code handling in the procedure, and you only do a quick check for the errors. And John, as you notice, remember the throws IO exception?
Yeah.
So there you didn't even have to check for an error. You just called the method. If it threw an error, you assumed it worked and just went about your business as though it worked. And then if you wanted to handle the error, you would have done so with an exception handler at the end of the procedure. So many times you don't even check to see if the error occurred if it's a system-defined error. So this is only the case, this if error is only for user-defined errors. Often system-defined errors don't even require the error check. You assume they work. If they don't work, you just go to the exception handler. So it's very clean because you just go through with your normal code as though everything's working fine. And then errors are handled in a particular place. And the other advantage is that if the exceptions are checked by a compiler, the compiler can basically tell you either handle it or specifically pass the buck to the calling function. So it's basically a bookkeeping approach to make sure that you at least thought about it. Okay, so the advantages are twofold. Advantages. Okay, one is that exception handling code is separated from normal code. Okay, when the two are interleaved, it can be difficult to read the code. Okay, and then the second thing is that it can encourage the user or programmer to consider all possible exceptional conditions and either make a decision to handle it or to pass the buck to a calling function. Okay, now C++ doesn't have that second capability, but Java does. So this is more of Java has the compiler do some exception checking. C++ does not.
So there are certain functions in Java, if you call them, it forces you to do the throw.
Yes. Which sometimes is incredibly annoying, but nonetheless is good to do it. So when you do parseInt, I believe that's a case where you have to explicitly handle it or else say you throw the exception. Okay. The I/O ones too, when you try to read from a file in Java, it won't let you get away with not handling it. You either handle it or you throw it. But if you don't, I'll get to that in a moment. Actually, I was going to do C++ first. And actually, I'm out of time, so next time we'll actually go into the way that C++ and Java actually handle exceptions. And probably that will take the entire, it's probably going to take the entire class period next time. Okay, so Thursday we'll actually talk about the exception handling mechanisms in C++ and Java.